In this video, I will discuss the cabinet that is inside the house, the electrical cabinet that contains the main controller board. And note that this cabinet communicates with the cabinet that's in the well house through this 1.5-inch conduit. So you might wonder why I use such big conduit. Well, there's a lot of signals and stuff. I have low voltage power. I have 12 volt, 5 volt, 3.3 going to the well house, and there are signals going to and from the well house. And I could have used smaller conduit, but it takes just as much work and almost the same expense to, for example, dig in the trench. It doesn't matter, it'd be the same for whatever diameter conduit. But this one thing, if I have this buried, if someone's digging around, if they hit this is less likely to break than like for example, a 3/4 inch or 1-inch conduit, because this is a little bit thicker, and it just would last, be more durable. So anyway, that's why I chose this larger conduit to connect these two boxes. This is the box that's inside the house, and then there's the electrical box out in the locker that has the relays, the power relays that actually drive the pumps and the electrical outlets out there. So anyway, let's look at what's going on here. We have, at the core of this is the main controller board, which actually drives through these relays. These are signal relays through fuses, protect the fuses, the relays. They go out to the panel outside to drive those power relays. These relays, they're signal relays. They can output up to 2 amps. Now they're actually going through 3/4 amp fuses, so it'll protect these relays if there's any shorts out in the panel outside in the well house. And these, for example, these can handle up to 2 amps each. Well, each of those power relays, the coils, the input coils on them is no more than 1/4 of an amp, so these can easily handle to drive those bigger relays. Plus, like I say, we have these I have a 3/4 amp currently, 3/4 amp fuses here, so if something did short, these would blow before it would be damage to these signal relays. The signal relays are being driven by these. So these are driver chips, and I'll discuss when I talk about the output section of this main board in more in depth. These driver chips drive these signal relays. So this chip can drive 4 relays, this one can drive 4, and this one can drive 4 relays. Each of these are all connected to the inputs to these driver chips are from the propeller microcontroller chip here. This is a propeller 1 microcontroller. I chose this type because it handles heat a little bit better, and from my experience it handles heat better, and it's pluggable. So that means a person can maintain this if something happened to it. There's the EEPROM chip. Down here is the programming connector. Okay, so anyway, the inputs to this board, there are 3. There have a 12 volts, 5 volt, and a 3.3. The 3.3 volt input to this goes for the propeller chip and to its EEPROM, and also to the outputs of these optical isolators here. 5 volts biases these driver chips. 12 volts actually is also a second voltage goes into these driver chips to drive these signal relays, and also 12 volts goes out from these relays to drive the coils on the power relays that are out in the well house. There's 12 volt. Now the 12 volt supply, I don't have it here right now. I have it in my desk, and it's coming through. So I have what I've got is a 12 volt line and some communication lines coming from my desk. And the reason that is I wanted to have the Raspberry Pi modules that are communicating through these cables on my desk, so it's easier for me to program at my programming desk rather than bring everything over to the panel here. But also the 12 volt supply is also coming across the room. The 12 volt supply is on my desk, and the 12 volts comes directly to here, to drive this, but also it goes to these two circuits. I hand wired this board. There's two circuits on here. This one right here and this one right here. These are these chips. The circuit is I use a simple switcher from Texas Instrument. These two right here. This one is designed to, circuit takes 12 volts in and has 3.3 volts out. That's going to power the microcontroller. And then this section right here has 12 volts in and 5 volts out. It biases these chips right here and this 7404 buffer chip right here. Okay, so there are three fuses here that protect the power supplies. And so then we have all these terminal blocks here. Now there are 6 terminal blocks here, and there's also the corresponding 6 out in the panel outside. So, and they're all matched accordingly. So for example, terminal block 1 connection position 1 is connected to through these cable to terminal block 1 position 1 out in the well house. Position 2 is also connects to position 2 on the terminal block out in the terminal block 1 out in the well house, for example. See, so these are all have corresponding matching out in the well house. So anyway, the highest voltage here, it's all low voltage, 12 volts maximum. So, but yeah, I kind of want to give an idea. So everything from going out this way is outputs to the well house down the bottom, and these are coming back from the well house from sensors and switches from the well house coming in through optical isolators right here. And I'll talk about those on the next video. So the next video I'm going to discuss the upper part section, the output section, and then the third video I'll discuss the input section and how that's all wired and biased and so forth. All right, so this just to give a context. Now, one mention, this board could have been out in the well house. This could have been out in the well house this year, and you wouldn't have to have all these wires, right? The thing is, it gets hot out there, and I don't want to have to. If you have it in the house here, I don't have to deal with heat because the house is air conditioned, and I don't need fans, cooling fans, and all that stuff. So, but also, if I have it in the house, I can develop it in here. Okay, so I can hook up my laptop to this right over here, and program the board right here, rather than having to take everything out into the well house and do the development out there, because weather can get kind of hairy sometimes. It could be snowing, it could be raining, it could be really windy and all that stuff. So, but if I have this in the house, I have control, regardless of what the weather's doing. I can do the development of the software and hardware right in here in the house. Right? If I had to replace this board rack, for example, I wouldn't want to do that out in the well house. I'd rather do it right here in a comfortable environment. See that? So anyway, okay, that concludes this video. I just want to give it a overview of this cabinet before I discuss further, more in-depth details on the controller board. So part 2, I will discuss the output section. Part 3, I'll discuss the input section of this board. All right, so anyway, why do I have a fiberglass cabinet instead of a metal one? Well, with fiberglass, I can Wi-Fi signals can penetrate this. If it was steel or metal, I may not be able to get the Wi-Fi signals into this. Because see, no, I'm not using Wi-Fi. If I put the Raspberry Pis inside here, I'd want to be able to communicate with Wi-Fi to them. Well, but having a fiberglass or a fiber or plastic cabinet, the radio signals can go through there. The Wi-Fi signals can get through that. So you wouldn't want to use a metal cabinet inside the house where you're communicating. And also, like out in the well house, if everything was out there, the Raspberry Pis and everything was out in the well house, then you better not have a steel cabinet. Otherwise, you won't be able to communicate Wi-Fi to the boards unless you had a signal, an antenna outside. So anyway, okay, that concludes this video, and I'll make another one. Like I say, there'll be 2 more of this, one for the output section of the main controller board and one for the input section.